Chapter 13, to which we talked about something. We talked about weak acids. So remember that weak acids are weak electrolytes, and they will set up that equilibrium, which means basically we will do an ice table to solve these. Um, so yeah, something like HF, going to dissociate into H plus and F minus here. Now we go through our ice table just like normal. Any other ice table, we'll have a Ka expression for it. And one of the ways you can recognize that it is a weak acid is obviously if it has a Ka value. So as we talked about before, only weak acids will have a Ka value. Strong acids will not have a Ka value. And again, that's one way you can kind of recognize it. The other way is we kind of listed 6 really strong acids, and by sort of the process of elimination, if that acid is not one of those 6, then it's probably a pretty safe bet that it's going to be a weak acid, and also a safe bet that you should be doing probably an ice table to solve it. The goal of this ice table is very similar to the last one, but really the thing that we're super interested in usually in these is the pH, which means we are usually interested in what this guy will be at equilibrium. And for the most part, the H plus concentration usually will equal the X value that you get. You'll solve these just like any other equilibrium ice table problem. You could try the assumption, as we talked about last time, as we saw last time. You definitely want to make sure you check it because not all time will the assumption work. So you want to make sure you check it with that 5% rule. You could also do the quadratic still. As I mentioned previously, you most likely will not come across too much perfect squares in this type of situation. Just for the way it's sort of set up, you usually will not end up with that sort of perfect square because usually you'll just have the weak acid over here, so you won't be really squaring it or anything like that. So usually it's going to be an assumption. It's going to be either quadratic as well. Once you get that, the additional thing that we typically do is just go right into the pH after we get that. And that will allow you to get the pH of that solution. We finish up talking about weak bases, and weak bases are also weak electrolytes, which means, again, you do need to do an ice table to solve that. So if you take something like ammonia. Now, as I mentioned last time, unlike the weak acids where I personally just show it breaking apart into H plus and F minus, you absolutely, as we've talked about a number of times, if you wanted to for the top one, include the water there. You again would just get H3O plus on the other side rather than H plus. It's really up to you, whichever way you want to do it. But with the writing of the equations here for the weak base, I definitely would kind of put the water in always, and it just think of it as the Bronsted-Lowry definition, and that a lot of times will help people sort of visualize where the OH minus comes from by the Bronsted-Lowry definition, where the water is going to act as the acid and donate the H plus over. That's going to get you your NH4 plus here and your OH minus. So again, as I mentioned at the end of the last time, this is really where a lot of people struggle is coming up with, again, the proper equation so that you can do the math. Once you have that equation, once again, obviously you would have a KB expression for this. And once again, you do know it's a weak base if it is a KB value associated with it, as once again, strong bases do not have KB values because they will completely dissociate or break apart into ions in solution. Once again, you're going to ice table this thing up like normal. Here, we're going to actually be looking for over here, probably our X value. The difference, though, is our X value here will not equal the H plus concentration. Here, as you can see from the table, it will equal the OH minus concentration, which means in these type of problems, you typically got to shoot for the POH first and then maybe subtract 14 to get yourself to the pH. So a little extra steps. Again, 2 very common errors people make on weak base problems. They write the equation wrong, and then when they do the ice table, they're in automatic mode of I got an X value, that's my H plus value, and they, instead of it being their OH minus concentration, and they kind of go into the pH with that rather than obviously the POH value. Any questions on any of that there? All right. So here's a table, and you have a similar one in your book. Again, there's some KB type ones. Most weak bases will be organic type bases. They have nitrogens and hydrogens and usually in it along the way. So why don't you give one a go here? What is the pH here? If you have a 0.15 molar solution of C2H5NH2, the Kb value there is 5.6 times 10 to the minus 4. So take a few moments there, work it out, get some type of pH value would be good. Okay, let's take a look, see how you're doing on this. So obviously here we got a couple things we could pull out for the problem. We got a KB, which should automatically scream to you a weak base, and when that's done screaming at you, it should probably scream at you that an ice table is probably the appropriate action here. Um, so we will start with our reaction. So we'll take our weak base there, C2H5 NH2 there. Once again, as I mentioned earlier, I would recommend putting the water into sort of your weak base type of equations. And again, all you have to do is just think about it like a Bronsted-Lowry definition. So we're going to send the H plus over, and all you got to do is attach yourself an H plus at the end of this. So we'll end up with NH3 plus. And once again, by the water losing the H plus, that is where we're going to make our hydroxide here. So again, uh, got to have some hydroxide on that side. That's going to give us a Kb expression of our products over our reactants. So we'll do C2H5NH3 plus times OH minus divided by our C2H5NH3 NH2. Once again, here water not included as it is a liquid, so still in equilibrium, so we don't include it. That's going to equal our 5.6 times 10 to the minus 4. We're going to do a little ice table action here. So we can go 0.15, a 0, and a 0. Change going to be minus x plus x plus x. Once again here, I'm ignoring obviously water since it's not involved. So why put numbers there? We'll get 0.15 minus x, x, and x in this case. Any questions on the ice table there? This is then going to go into our expression here. So we will end up with x squared divided by 0.15 minus x equals our Kb value of 5.6 times 10 to the minus 4. It is a small value of K, so you can assume x is equal to 0. And if you did, of course, you checked it and saw it was 6.1%, which made you really sad. And it's a bad assumption in this case, right? So because this is a bad assumption, we then need to solve it using our quadratic. And we're going to then multiply that to the other side, and that will get us x squared is equal to, looks like 0.000084 minus 5.6 times 10 to the minus 4x, bringing everybody to the same side, x squared plus 5.6 times 10 to the minus 4x minus 0.000084 equals 0 in this case. That obviously is going to be our A, B, and C in this case, right? Or A, B, and C. That's going to go into our quadratic. So let me just flip the page maybe. Whoops, let's go. The page, and we'll just do it here. We just rewrite that there. X squared plus 5.6 times 10 to the minus 4x minus 0.000084 equals 0. So going into our quadratic, that'll be negative 5.6 times 10 to the minus 4 plus or minus our b squared minus 4ac. If you do all that inside the square root, you end up, I believe, with something like this, 0.000336 314, I think. If you square root it, you will end up with, wrote it down, what did I get there? 0.01834 looks like. 834. That's going to all be times by 2 times a, which is 1 in this case, so that's going to be 2. Doing our plus wave first, looks like we will end up with here an x value of 0.00889 Or if you go the minus direction, you're going to end up with a negative number here of negative 0.00945. Looking back at our ice table here, we could obviously see the OH minus equals X. So clearly the negative number not going to work very well for us. That means in this case, X does equal the hydroxide concentration. Once again, the hydroxide concentration and not the H plus concentration. That's going to allow us to go into the POH minus the log of that number, 0.00889. That's going to get us here minus the log 0.00889. Looks like a 2.05 POH. We then could just subtract 14 there and get our pH. And we're going to end up with 1195 on that pH, I think. And that is a basic pH, and as we would hope so with a weak base. Any questions on that? Yes. The truthful answer is it can happen. Not in this application, probably, because again, this application, you're going to be looking for the pH and the POH and all that. And usually the H plus or OH minus concentration does equal X. There is a place, for example, when we talk about KSP, we just talked a little bit about that earlier. We'll talk about it later. There is potentially a case where you could end up actually with two negative values that came out of the quadratic. And actually, when you put it into your ice table at the equilibrium, it will actually turn it into a positive number and it will be okay. So it can actually happen, very rarely, but it can actually happen. Yeah. Yeah. Yeah, technically, you could use it. That's really right at the point where it's okay, I guess, to use it. Ideally, anything above 5 you don't really want, so it's kind of like it would be okay in that case. Yeah. Hopefully, you probably won't come across too much that it hits exactly on 5, but yeah. So, but obviously, the closer you get to 5 or higher, obviously, but definitely the closer you get to 5, then it's not such a great assumption per se. There's a lot more variability as you get closer to that 5. Yeah, there's that. And really, that's all. Our check of our assumption is really that percent ionization that I think we talked about last time as well. That's really what you're calculating when you do that. And again, as you get above 5% ionized, again, that's a little bit more significant, and that's why we can't kind of take those assumptions greater than that. Other questions? So as you can see here, basically weak base works the same way as weak acid, which works basically the same way as any other equilibrium. But again, you just got to be careful of those small things that people screw up on. Again, thinking it's the H plus concentration, and again, not writing those things correctly is a very, very, as I mentioned, common error. Any questions on that there? So far we've seen two types of sort of equilibrium constants involve acids and bases. We've obviously seen our Ka value, and we've also seen a Kb value. Obviously, the Ka value is for an acid, a weak acid. Kb value is for a weak base. Now, you may be wondering, maybe how do you know which one you should be using? And the very simple answer to that is if you write your equation correctly or you have the equation written correctly and you look on the product side and you see H plus or you see H3O plus hanging out over there and you need to do a calculation with a K value, that should be an acid. So you should be using a Ka value. If you write your equation correctly and you see hydroxide hanging out over there, then it definitely should be a Kb situation. So that's again why it's really important to be able to write those equations correctly, because it does give you a lot of information and helpfulness when you're trying to do the calculation. But that's really how you should know if you should be using a Ka or a Kb. Now you may be asking, why is that important? And the reason that's important, as we'll talk about shortly, is there are certain problems where they will actually give you in the problem the wrong K value. They'll give you the Ka value when you need the Kb. They'll give you the Kb value when you need the Ka value. So being able to recognize what you should be using in a calculation is really, really important. And that is the best way to recognize it is what you see on the product side. H plus, H3O plus should be rolling with the Ka. OH minus on the product side should be rolling with the KB. Now, these are two equations, and as we talked about earlier, when you add two equations together like we can here, we're going to get some things canceling out, and what's going to cancel out is pretty much everything except our good friend, water. And if you take a Ka, or weak acid, and a conjugate base there, and it's Kb, and add it together, you basically make water, which we also know has a K value associated with it, which is Kw. And what that allows you to do is when you add these two together, equations, what you do with the K value is, remember, you multiply the K value, do not add them. And that gives you this really important sort of relationship here. The Ka times the Kb will equal the Kw. And that Kw is the same Kw that we used in the previous calculations, 1 times 10 to the minus 14. So what this allows you to do is, if by some chance you are given the incorrect K value, you got Kb when you need a Ka, you can use Kw to switch it to what you need, or vice versa as well. So that's a really important sort of relationship that you can kind of switch between a Ka and Kb using Kw really easily to do so. Any questions on that there? Let's talk a little bit about acid strength, and there's a couple of different types of acids. One type of acid is one that does not have oxygen, and these are typically your group 7 acids, your HF, HCl, HBr, HI. And one of the things that people may think about in terms of it being a strong acid versus, say, a weak acid is the electronegativity difference between the hydrogen and the other element that is there. And it turns out that when we look at this type of acid, it does not contain oxygen. The overwhelmingly thing that we look at is actually not electronegativity, but it's actually bond enthalpy. And if you remember what bond enthalpy is, it is the energy required to break a bond, basically. Yeah. So how much energy you got to put in there to break a bond. And when you look at the bond energy between HF, HCl, HBr, and HI, which are all acids, hydrofluoric acid, hydrochloric acid, hydrobromic acid, hydroiodic acid, what we actually see is as you go up the group, the bond enthalpy increases. The delta H value there increases. And what that means is it takes a lot more energy to break the bond between the hydrogen and the other element. Why is that important? As you hopefully know, when you break this bond, that is the hydrogen that gets released, and that is what makes something an acid, right? The ability to release that H plus. So if the HF bond takes a lot more energy to release the H plus than the HI bond, the HF is going to be a much weaker acid than HI, because HI is just going to let go of its H plus a lot easier. HF is going to hang on to its H plus a little bit longer and make it much weaker. So in terms of strength, acid strength in group 7 actually increases as you go down the group, because the bond energy decreases as you go down the group, and that's going to allow that H plus to come off a much easier, making it a much stronger acid. That's why hydroiodic acid is actually a stronger acid than hydrobromic acid, which is a stronger acid than hydrochloric acid. And that is why when we get to hydrofluoric acid, there's a big jump in bond energy to break that, and that's why HF is actually the weakest acid of everybody there in group 7. So when you're looking at acids with no oxygen, it's actually the bond enthalpy or bond strength that is the overwhelmingly determining step of which one is a stronger acid. Any questions on that there? Now, when you do have acids that actually do contain oxygen, there are a couple of things that you look at in terms of determining which one is a stronger acid versus which one is a weaker acid. And again, you can kind of see the pattern there on that one. Now, when we look at what are sometimes referred to as oxyacids, oxyacids are pretty much what it sounds like. They are acids that contain oxygen. They typically also contain polyatomic ions in there, which is where the oxygen comes from. And depending on the situation, we will look at either electronegativity, And a reminder that electronegativity is the ability of an atom to bring electrons towards itself. And when we talk about electronegativity, it increases which way on the periodic table? Up and to the right, right? So it increases up and to the right, decreases down. Fluorine, right? Fluorine is the most electronegative element that you could have. The other thing that we look at is oxidation state or oxidation number, which you might have dealt with when you did all those redox stuff maybe in the previous class. And we may look at oxidation state. So it all really revolves around this bond. Most oxyacids will contain this OH bond, and that OH bond is a polar bond, which means the hydrogen is more partially positive, the oxygen is more negative. So this bond is weakened to begin with, and that is the hydrogen that comes off in most oxyacids to make it basically an acidic solution. That's the hydrogen that is released. So let's take a look at when we would look at which one. Let's say we were looking at each of these acids here, HClO3, the chloric acid, and BrO3H there, or HBrO3, which is bromic acid. Now, in this particular case, the oxyacids have different central atoms, but they are from the same group, and they actually have the same oxidation number. So in case you're not sure how to calculate oxidation number, let's just go through it really quick, and we definitely will do it a little bit later on when we get into the redox storage chapter more. But in most cases, the oxidation number or state of oxygen is -2. So this would be a -2, this would be a -2, this would be a -2. Hydrogen's oxidation state is typically +1. So if we add all those up, that's -6. -2, -2, -2 is -6. +1 is a -5. This acid is neutral, so the chlorine here is rolling with a +5 oxidation state. Now, as you may remember, or you may not remember, or we'll talk about later as well, oxidation states are not the same as the charges you normally associate with some of these elements in an ionic compound. This is not an ionic compound. These guys are sharing electrons, and in this configuration, chlorine's rocking with a plus charge there rather than the normal negative charge it gets in an ionic compound where it's receiving electrons. So in this case, it is sharing electrons here. When you look at over here, the oxygen again going to be -2, -2, -2. Hydrogen once again going to be +1. So the oxidation state here on our bromine to balance it out to 0 is going to be +5. So in this case, the central atom both have the same oxidation number, which means you cannot use that to compare acid strength because they're obviously the same. So in this situation, what we compare is electronegativity. So in a situation where we're comparing two acids, they both have the same oxidation state in the central atom, you want to look at electronegativity. When we look at the electronegativity between chlorine and bromine, we can see that electronegativity increases as you go up. And that means that chlorine is actually more electronegative. So the idea here is this: because chlorine is more electronegative, this bond right here is polar to begin with, so the electrons are heading in this direction. Now with the chlorine being more electronegative, it's going to pull those electrons closer and closer to it. What that is essentially going to do to that OH bond is it's going to weaken and weaken this bond as those electrons start migrating in a lot further away from the hydrogen, going to make this hydrogen pop off a lot easier than the one over here because the bromine is less electronegative. Still going to do the same thing, going to pull those electrons in, but not as much as the chlorine is going to do. So it's going to be a little bit harder for the bromine to release that hydrogen in comparison to the chlorine, because the chlorine is going to be sucking those electrons in closer to itself, making the hydrogen more and more electron deficient and more positive, and it's going to pop off a lot easier. So in comparison of these two here, because the chlorine is more electronegative, that would be our stronger acid. And in this case, the HClO3 would be a stronger acid than the HBrO3. Any questions on that? So tyon electronegativity, you turn to tyon oxidation number, you turn to electronegativity to compare. Higher electronegativity, stronger acid, because the H plus is going to be able to be popped off a lot easier because of the difference in electronegativity. Any questions on that there? All right, then let's take a look at the opposite situation, which is we have kind of the same central atom, but we have different groups attached. And because we have different groups attached, we actually will obviously have the same electronegativity because they're all chlorine as the central atom. So chlorine obviously has the same electronegativity in each of these. So we cannot use electronegativity to help us decide, but here we would use oxidation number. So once again, in terms of our oxidation number, this would be -2 for the oxygen, +1. That's a -1. The chlorine here would be +1 to balance it out to 0. Here, oxygen -2, oxygen -2, hydrogen +1. That's -4, and +1 is -3. The chlorine here is going with a +3. This is the one we just did, -2, -2, -2, and +1. That's a -6 plus 1 is a -5. Chlorine here +5. And lastly, -2, -2, -2, -2, and +1. That's a -8 plus 1 is a -7. That means the chlorine here is going to be a +7 in this case. Basically, it's the same idea because the chlorine at the bottom there in perchloric acid has a much higher positive oxidation state. Opposite attract, right? So negatively charged electrons going to be pulled in closer to that bigger positive charge. And what that's going to do is weaken this bond right here and allow that hydrogen to come off a lot easier than the +1 attraction that those electrons are filling in this bond. Remember that when we talk about opposite attraction, the strength of that attraction increases with the size of the charge. So something with like a +7 charge is going to pull things a lot more than something with a +1 charge. Even though they're both positively charged, it's going to have a greater pull on those electrons. So in this case, this would be our strongest perchloric, our next strongest, and the hypochlorous acid would be our weakest in this case based on oxidation number. Any questions on that? So this is the opposite sort of situation. Same electronegativity. We look at oxidation number here. Any questions on that there? All right. The next thing we're going to talk about is salts. So just a reminder that when you take a acid and you react it with a base, you typically get two things. You typically get a salt and water, right? Famous little saying there. And a salt is an ionic compound. Now, the importance of the salt and what we're going to be talking about is in some cases, the salt may continue to react with the water and affect the pH of that solution. And in some cases, the salt will not react with water and will have no really effect on the pH. So how do we know sort of whether or not a salt will continue to react with water? It has to go back to that relationship that we talked about earlier on in this chapter. So just to revisit it, if you have an acid and its friend, the conjugate base, if that acid is strong, remember that the relationship is the conjugate base will be relatively weak. If the acid is weak acid, its conjugate base will be relatively strong. What that means in this context of salts is if it is weak, it will not react with water. If it is strong, it will react with water. So that is what we're talking about here in terms of that relationship. Same thing with our base and our conjugate acid. If you have, again, a strong base its conjugate partner is going to be relatively weak. And if you have a weak base, its conjugate partner is going to be relatively strong. And again, what we're talking about here is the reaction with water. So if it is weak, it will not react with water. And if it is strong, it will react with water. So a reminder that when we're talking about a strong conjugate acid here or a strong conjugate base here, we are referencing the idea that it will react with water. It is not as strong as a strong acid or a strong base. It's just strong in the sense that it will continue to react. Any questions on those relationships there? So let's take a look at something here just to kind of see what we're talking about. Now, there are some neutral salts, and most neutral salts contain an alkali metal or an alkaline earth metal. So that is group 1 and group 2 on the periodic table. So if you see something that comes from group 1 or group 2 on the periodic table, that is going to be a neutral salt. It will not really react with water. The exception is beryllium there. So if we have something like sodium chloride, which is a salt, and if we have sodium chloride in solution, we basically have two ions floating around, sodium ions and chloride ions. Now, one of the helpful things when you're dealing with salts is to perhaps try to figure out where the salt came from. Yeah. So this salt came from usually a reaction of an acid and a base. If you had to guess what the acid might have been, what do you think it might be here? I see Cl there. What do you think the acid would be? How about HCl? Yeah. HCl reacting with sodium hydroxide will do a double displacement reaction, right? So these guys are going to come together. These guys are going to come together. That is going to form your salts there, sodium chloride, right? And H plus and OH minus makes water. Yeah. That's your water. Yeah. So really here, this salt most likely was generated from a reaction of HCl and sodium hydroxide. So let's start with the HCl. When HCl breaks apart, it is a strong acid, right? And it'll break apart into H plus and Cl minus. This is our strong acid. Over here would be its conjugate base, right? The relationship between those two. So if HCl is a strong acid, Cl minus will be a strong or weak base. It will be weak. It is the opposite relationship here. Yeah. And if it's a weak conjugate base, will it react with water? It will not react with water. So because the Cl minus part here most likely came from a strong acid, it is not going to continue to react with water, and it will give you a neutral pH. You would expect the pH there of Cl minus floating around to be 7. Yeah, so neutral pH of 7. Yeah. Now, when we look at sodium hydroxide, and that breaks apart into a sodium ion and hydroxide. This is our strong base. And this sodium came from a strong base, which means it's going to be relatively weak in this case, right? And because it's weak, it will not react with water. And it also will be neutral as well. So the reason it says up there, any salt that contains group 1 on the periodic table and group 2 on the periodic table, there really is a reason for that. And that is, as we talked about, what things are made in group 1 and group 2 on the periodic table. That's usually where we can find our strong bases. Yeah. Things like sodium hydroxide, potassium hydroxide, lithium hydroxide, calcium hydroxide, strontium hydroxide. So because a lot of strong bases come from group 1 and 2 on the periodic table, when you see them in salts, that means they're going to be weak and not react with water. and will give you a neutral pH. So if you have a solution that contains sodium chloride, because it basically comes from a strong acid and a strong base, you will not get a reaction with water, which is known as hydrolysis, and it will end up giving you just a nice pH of 7, a neutral pH in that case. Any questions on that? Now let's say we took this salt here, a little sodium acetate. Yeah. By the way, salts are strong electrolytes, which means when they are swimming around in solution, they are not staying together. They're going to break apart into ions like a sodium ion and an acetate ion. And again, 100% you're going to have these ions floating around. So when you look at a salt, once again, you want to really determine whether or not there's something there that will react with water and go through this hydrolysis reaction. So when we look at each of these ions that were formed as a result of this salt, we have sodium, which, as we just talked about, most likely came from sodium hydroxide, which is a strong base, which means this guy is still a neutral salt and will not react with water, right? Because again, it comes from a strong base. It's going to be relatively weak, and sodium is found in group number 1 on the periodic table, which tells you it's going to be neutral. How about acetate? Acetate most likely came from what acid? If it ends in ate, your acid will end in ic. So instead of acetate, it is our friend acetic acid. Yeah. Vinegar. Yeah. So acetic acid is most likely the acid at which acetate came from. So is acetic acid a strong acid or a weak acid? What do we think? Got a 50-50 shot on that. What do you think? Not everybody at once. It's really overwhelming when you all answer at once. Yes. What do we think? Well, let's just start with our strong acids. Which 6 are strong acids? That's hydrochloric acid, right? That's not it. Nitric acid, not it. Perchloric acid, not it. Sulfuric acid, not it. Hydrobromic acid, not it. Hydriodic acid, not it. I'm out of strong acids. Did I hit it? So it's probably a weak acid. Yeah. So again, knowing those 6 strong acids helps you in situations like this, because you could figure out that it's probably a weak acid, and it is a weak acid. And when this breaks apart, obviously here we get H plus and acetate are the ions that you get here, which means that this would be its conjugate base. Now, since acetate comes from a weak acid, will acetate be a strong or weak conjugate base in this case? If it comes from something weak, it's going to be opposite, which is strong. Yeah. So this is going to be a strong conjugate base in the sense that it will react, yes, with water. So because acetate here came from a weak acid, we know that it will react with water. So let's do that reaction, shall we? We'll take our acetate. I am not concerned at all about the sodium because it's neutral. It's just hanging out. It's kind of like a spectator ion. It ain't doing much. It's going to react with water. So now I have to decide, how is it going to react with water? Well, I know that the acetate came from a weak acid, which means it's a conjugate base. So when it reacts with water, it should react as a base again. And the Bronsted-Lowry definition of a base is it will donate or accept an H+. It will accept the H+. So it's going to accept the H+ there from water. The result of that there is you will always make, by the way, where it came from. So you will make acetic acid. Yeah. And when that water loses the H+, it will make hydroxide. First off, any questions on that calculation there, or that reaction? And again, like I said, you always make really where it comes from. If you had to make a bet, would you expect this solution to be neutral, acidic, or basic? What do you think? What is really staring at you in that equation that's like jumping off the screen? On the right-hand side of the equation, what's there? I see OH minus, yes? And we associate OH minus with a base. So because this is going to produce hydroxide, this solution is going to be a basic solution before you even do the calculation. You should end up with a basic pH if you go through the calculation. Hence, as well, why it's important to be able to write these things. Yeah, so you want to make sure you know how to write these things correctly. First off, any questions on that? By the way, if I wanted the pH of this, I would do an ice table. Yeah. And when I get through my ice table and I get to my K to solve for everything, what type of K should I be using? I should be using a KB because, again, we have hydroxide there on the right-hand side. By the way, if you did this problem, you would not have the KB value. You would have the Ka value for acetic acid. So how can I get the Kb value? That is what we just talked about. That is what the whole Ka times Kb equals Kw. You most likely will have to use this to get the correct Kb value to do this. Super common error, people just use the K value they gave you in the problem, and it will be the wrong one. And this is the type of problem. These are known as hydrolysis problems, which are these salt problems. These are the problems where they definitely give you the wrong K value. You'll have the Ka in this situation for acetic acid when you actually need the Kb, and we'll see the opposite happen as well. So that Ka times Kb, Kw definitely comes into play very, very importantly here in these salt type problems. Say it one more time. I missed the first part. Yeah, so the part that reacts with water comes from the salt. So that sodium acetate basically is the salt. And the salt's really just an ionic compound. It's got a cation and an anion. And in this case, it's only the negative guy, the acetate part of the salt, that will go through hydrolysis and react. The sodium part will not. So that is the part of the salt that's actually going through hydrolysis. So that acetate is actually part of the salt that's actually going through hydrolysis. Yeah, the ice table would be just this bottom part here, obviously with numbers, and you would solve it like normal. But the reaction, if that's what you're asking, is once you determine that the salt, one part of the salt will go through a reaction with water, it always is water it's reacting with on that side. And that's always that's really what's going to generate the hydroxide is that reaction with water, basically. Yeah. Other questions? Yeah. All right, so that is what we see down here. We have our basic salt, and I got an extra hydrogen on that guy there. And again, going to produce that hydroxide. Now, in addition to basic salts, and basic salts usually come from the presence of a weak acid, or they came from a weak acid, usually will generate a basic salt. We can also have an acidic salt, and an acidic salt is basically the opposite. If we had a salt like, actually, we'll choose this one here. Let's use this page. There it is, I think. There it is. So we'll look at NH4Cl, and this is a salt. And if we have NH4Cl, again, as it's a salt, it will break apart into NH4 plus and Cl minus. And once again, once you have the salt, what you want to determine is, will any of it go through hydrolysis, which means will any part of this salt react with water and go through that hydrolysis? So we obviously can eliminate the chloride, as we saw earlier. The chloride part of this salt comes from probably something like hydrochloric acid. By the way, you would generate this salt, if you're not sure, by probably the reaction of hydrochloric acid and ammonia. And the ammonia would accept the H plus, and that is what's going to produce our NH4Cl, which you can either keep together or break apart. So the Cl minus comes from the hydrochloric acid, which is a strong acid, as we talked about before. That means here our chloride is going to be neutral and not really do anything with the pH. That leaves us our NH4 plus, which comes from ammonia here. And ammonia is a base. It is what type of base? It is a weak base. Yeah, it's probably the most popular weak base you ever met. And that is definitely a weak base. That means over here, its partner, the NH4 plus, would be the conjugate acid, right? You got a base on one side, partner on the other side, right? The opposite there, conjugate acid. Because the NH4 plus comes from NH3, which is a weak base, this is going to be a relatively strong conjugate acid, and it will react with water in this case and go through a hydrolysis reaction. So out of the two parts of this salt, it is the NH4 plus that will go through hydrolysis. So the reaction that we would have is NH4 plus, once again, going to react with water. And I do know how it's going to react because it came from a weak base. It's going to be an acid, which means when it reacts with water, it's going to react as an acid. The Bronsted-Lowry definition of an acid is it will donate the H plus over. And when it donates the H plus over, you will once again always make where it came from. So that thing really came from NH3, and you will make it. When the water accepts the H plus, you will make H3O plus in this case. And once again, without having to do any calculation, would you expect this solution to be acidic, basic, or neutral? This solution should be acidic because you have H3O plus being formed. So in this case, the salt will produce H3O plus. It will make that solution acidic because the H3O plus is being produced in this case. Same deal, if you were going to solve for this, you're going to do an ice table. What type of K should I use in this calculation? This should be a Ka, yeah, because it is acidic here, and you have H3O plus. Once again, in this problem, if you were given it, you would be given the Kb value, most likely for NH3. And again, you can use that Ka times Kb to flip it around. Any questions on that? So if your salt basically came from a weak base, it will go through hydrolysis and react with water, and it will produce basically an acidic solution because it is producing H3O plus. Any questions on that? Now, there is another way that you can actually produce an acidic solution, and some metals, especially some transition metals that have a big positive charge, +2, +3s, can actually react with water and produce H plus or H3O plus in this particular case. Aluminum is an example of that. Chromium, beryllium, and some other transition metals can react with water to produce H3O plus. So just to illustrate how that sort of works, let me find a much better spot to draw that. So what you basically have there is aluminum with 6 waters attached to it and a +3 charge. So if you kind of draw that out, you have an aluminum and you have 6 waters attached. They are attached to the oxygen, by the way. I'm not going to draw it perfectly like that. I'm only going to draw one of the waters out. So you got basically one of these waters out. And what happens in this particular case is just a regular old plain water is floating around in the solution. And what it will do is it will take one of those hydrogens off of the water that's attached to the aluminum. And when it does that, this, by the way, is a complex ion. This also is what it means when you put aluminum with an aqueous little symbol on the bottom of it. It has water attached to it. And the result of that is when it takes that H plus, it will form H3O plus, which is going to make the solution acidic in this case. Now, you may be wondering how you get to that weird formula that was at the end there. Well, you still have your aluminum, and you still have 1, 2, 3, 4, 5 waters still intact. This guy just lost his H, leaving him hydroxide, which is OH minus, and you'll be left with 1 OH. And the overall charge will go from +3 to +2 because -1 from hydroxide and +1, 3 leaves you a +2 left over, and you will form that H3O plus in that case. So certain small metals with larger positive charges can sort of use their complex ion there and react with water and produce H3O plus is another way you can kind of have an acidic salt. Again, like I said, some transition metals can do that, like copper, for example, and some other ones, nickel and aluminum, and those guys can kind of do it as well. Any questions on that salt? All right, so let us take a look at some of these problems here and see what's got going on. All right, so take a moment here. What is the pH of a 0.45 molar KCl solution? Okay, so let's take a look at this. We want to look at the salt here, which is KCl. And KCl, which is a salt, will break apart into two components, K plus and Cl minus. So really what you want to think about is, will any of those guys go through hydrolysis and react with water? Would I expect the potassium to react with water? Potassium should not, because it is group number 1 on the periodic table. It basically comes from KOH, which is a strong base. And because that is group 1, it will not react, it is neutral, right? How about chloride? Will chloride react with water? Chloride most likely came from what acid? Hydrochloric acid. Hydrochloric acid is still a strong acid, which means will the chloride react? It will not. It's going to be weak, right? So this will not react because it comes from a strong acid. And that will also be neutral. Good news here, the pH of this solution should be a pH of 7, no calculation needed, as both parts of this salt are neutral salts and they will not go through hydrolysis, will not produce hydroxide, will not produce H3O plus, and should give you a neutral solution. Any questions on that there? All right, let's do one that does involve a calculation. This one does. Consider a 0.3 molar sodium fluoride solution. The Ka value for hydrofluoric acid is 7.2 times 10 to the minus 4. What is the pH of this solution? Yeah. So take a few moments there, see what you come up with. I'll give you a hint. It involves an ice table. Let's try that. Yeah. Okay, let's take a look at it since we're getting to the end here, just to kind of go through it here together. So we do have sodium fluoride, which is a salt. And again, this sodium fluoride will break apart in solution into both ions here, which is a sodium ion floating around and a fluoride ion floating around. Now, again, you want to determine whether or not any part of that salt will react with water and go through hydrolysis. At this point, we've talked a lot about sodium. We hopefully should still know we really don't have to worry about sodium, right? Because it's, again, a neutral salt, group 1 on the periodic table, comes probably from sodium hydroxide, so we don't have to worry about that. That leaves us F minus. So we want to think about where would F minus probably come from. I would say that very commonly people just overlook what's in the actual problem. And if you read the last part of the problem here, it says that the Ka value for HF is 7.2 times 10 to the minus 4. So if I had to venture a guess, I would probably guess that that F minus comes from this guy right here, which is HF. Now, because it has a Ka value, that should automatically tell me this is what type of acid, strong or weak. That was not the hard question. It is a Ka is for what type of things? Things that are weak. Yes, that's a weak acid. Yeah. And because this is a weak acid, and this is most likely where that came from, this would be its conjugate base, and it should be relatively strong in the sense that it will react with water. So by that process of elimination, we now know that it is the F minus part that will react with water. So that is where we're going to get our reaction. It's going to be the F minus is going to react with water. Now, it also tells us because it comes from this weak acid, this will be a base, and that is how this guy is going to react with water. It's going to react as a base, which means it's going to accept the H plus. Also, you should not overlook just common sense, which tells you, hopefully, this thing does not have a hydrogen to give, so there's no way it could be act as an acid, right? So F minus doesn't even have a hydrogen, so there's no way it could give away something it doesn't have, right? So the only thing it can possibly do is accept the hydrogen. And when it does so, it will always, as I mentioned, form where it comes from, which again, if you struggle with writing the equations, all you have to do is look at the problem. And now you have half of what you just made on the other side right there in the problem. So, by the way, it also should produce hydroxide in this case when the water gives away the H plus. So without doing my calculation, I should definitely know when I do calculate my pH, it should be acidic, basic, or neutral in this case. It should definitely be a basic pH because we are producing hydroxide in this case. So let's do that calculation here. Just going to scratch that out. Initially, we have 0.3 molar. This is going to be 0 and 0. Change going to be minus x plus x plus x. And that means at equilibrium, 0.3 minus x, x, and x. So a pretty standard table. Any questions on the table? Just like normal, this is going to go into my K expression, which is my products, which is HF times OH minus divided by F minus. By the way, this is a K, A, B, C, D, F, G. This is a K, B, right? It's a KB because, again, we're producing hydroxide here. And looky, we do not have a KB given to us, but we have the Ka. So once again, this is where we're going to use that relationship to get the Kb value. Do it here, maybe. The Kb value will be our 1 times 10 to the minus 14, which is our Kw, divided by our Ka value here, 7.2 times 10 to the minus 4 in this case. And that will get us here 1.4 times 10 to the minus 11. So I'm going to pop that right there for my proper Kb value. That means now I have the right number there that I want to use in this calculation. Putting in my values, x squared divided by 0.3 minus x equals 1.4 times 10 to the minus 11. That definitely is a small value of k, which means I could assume x is equal to 0 in this case. That will give me x squared divided by 0.3 equals 1.4 times 10 to the minus 11. I'm going to multiply to the other side and then take the square root. And if I do that, I'm going to take the 1.4 times 10 to the minus 11 times it by 0.3 and take the square root of it. This is going to give me an answer for x of x is equal to 2.04 times 10 to the minus 6. I do need to check this, right? So we're going to take that value. We're going to divide it by 0.3. We're going to times it by 100%. And the check here is good. It's not even 0.1%. It's really good in this case. And we should have no problem on that. All right, so now that we have the x value, the other thing we want to remember is when we go to our table here, the x is not the H plus concentration in this case. The x is actually the hydroxide concentration. So x equals the hydroxide concentration. We're going to go into our POH minus the log of 2.04 times 10 to the minus 6. And that is going to get us here a 5.69. Now, by some chance, if you thought this was your pH, it should not make sense to you because that would be technically an acidic pH, and your equation says it should be basic. So again, just in case you kind of screwed up there, to get to the pH, we're just going to take our 14 minus 5.69, going to yield us an 8.01, I think, 8.31. And a pH of 8.31 definitely is basic and does make sense in this case. Any questions on that calculation there?